Hi bio students, I'm going to walk you through a couple of important things about water based on the observations that you've been making in class. So let's go and start with this presentation. So in class you have been doing a couple of hands-on activities or maybe at home. The first one I want you to think about is how many drops can you put on a penny and what did it look like? So I did this, so if you weren't able to, you can just look at my observations. Some people are able to get more drops on, some people are able to get less. Kind of depends on your dropper sometimes. I went a little quick, so I didn't get too many, but I want you to look at the structure or the shape that you see on top of that penny. So it's got a very interesting shape. Some pennies are better depending on if they're cleaner or not. But what I hope you noticed is that you've got this kind of bubble shape on the top of the penny. And the reason that we see this is because of cohesion. So water has polarity, okay, and it'll form hydrogen bonds with other water molecules. So what does this look like? You can see down at the bottom, there's this animation. The little yellow dotted lines are hydrogen bonds. The reason water can form hydrogen bonds is because water has polar covalent bonds. And what is a polar covalent bond? This is an unequal sharing of electrons in a covalent bond. So water is very, very special. And because oxygen is super electronegative, it's an electron hog. It'll pull most of the electrons from the hydrogen that it's supposed to be sharing with hydrogen. It'll pull more of those electrons towards itself. And because electrons are negatively charged, that'll create this charge distribution or this polarity in the water molecule where there's a partial negative charge closer to the oxygen and a partial positive by the hydrogens. So you had, because of this, we can, water has a lot of really cool properties that enable life on this planet. So it can provide surface tension, so that hydrogen bonding can allow things to kind of actually float on the surface, which is super important. Because of this, ice can float. So when it forms those hydrogen bonds in the solid state, it actually spreads out the water molecules, and this makes the ice less dense and it'll float, which enables life to live underneath it or on top. It doesn't get smashed by the ice. Also really great for regulating temperature. I will not ask you to have to be able to explain this, but it's really important that it does it. Because water, it's really hard to break those hydrogen bonds, even with the addition of a lot of heat from the sun. This really regulates the temperature in us. It also regulates the temperature in bodies of water, and it really keeps our planet at this really livable temperature. If we didn't have enough water, we wouldn't be able to live on this planet. It really is really important for that. And also it's a really great medium for dissolving solids. So if you ever put sugar or salt inside water, because you can have those ions or dissolved solids in there, it's really good for that. So what about with detergent? You probably noticed with, oh, I didn't animate that one, whoopsies. With detergent, you probably saw it was a little bit different. So let me play this video for you. Okay, put a little bit of detergent on top of the penny. And detergent is a very interesting molecule. It's kind of, the reason we wash dishes with detergent is it kind of has properties that are similar to water, but then also kind of more like fatty based things. As you can see, it got clearly less drops, and it didn't get that really big kind of bubble of water on the top. There was no way that the water could hydrogen bond to each other because those detergent molecules were in there. So detergent disrupts that, and as a result, you don't see that cohesion that we saw in the previous slide. This happens when you have other solutes in, so say for example salt. When salt is in water, it makes it really hard for it to form those hydrogen bonds or even freeze. That's one of the reasons why salt water can get a little bit colder, or we use salt in the winter to kind of prevent ice formation. It also works with, it stops like the temperature deposition as well, but really kind of cool that this can happen. But those hydrogen bonds, when they can form in a pretty pure substance, and mostly water, it's really great for living things. So let's talk a little bit more about some other properties. So you had to put a capillary tube in water, and we saw something else really interesting happen. So I'm adding a tiny bit of food dye. Some of you may have added it, some of you may not have. This is really just to help you see the water better. I didn't want to have you do this with a penny. I didn't want it to disrupt any of those really nice hydrogen bonds. So here goes the capillary tube, and the capillary tube is made of glass. And I hope that you're noticing that the water level in the capillary tube is rising above the surface. And this isn't a pressure thing, okay? This water is fighting gravity. So why is that happening? Okay. This has to do with another important property of water. So water is really good at adhesion. So cohesion is the attraction of water to other water molecules. Adhesion is the attraction of water to other molecules, typically through hydrogen bonding, because water can form those hydrogen bonds. So a lot of times when other molecules are polar, like water, we're going to see that this is happening. Glass, for instance, is attractive to water. That's why when you're measuring with a graduated cylinder, you see that meniscus, the attraction of the water to the glass. Here, because the tube's so small, the water can actually stick to the glass and stick to each other, and it can rise up against gravity. This is really important for plants. They use a lot of this special adhesion and cohesion to get water up hundreds of feet in a tree with the help of evaporation as well. You study more plants later, you'll learn about transpiration. But this adhesion, the sticking of water molecules to something like cellulose, or in this case glass, is really, really important for life. So the last thing that you, hands-on activity you had to do was to do a little bit of mixing. So what happens when you mix water and oil? You've probably seen this before when you've maybe mixed salad dressing. So this is the opposite direction. I don't think you usually see water being put into oil, which is kind of fun. Usually we put oil onto water. So here are some drops of green water from before. Use the same water. You can see it falling into the oil. Some of it's getting a little bit stuck to the surface where it's interacting with the air. You'll see that kind of, in a second, those little guys will kind of separate from the surface. The one's a little bit stubborn. There you go. So water is more dense than oil, so the water is gonna sink down to the bottom, and you can see it forms those nice little circles, those spheres. Sometimes when it's just oil and water, we call those micelles, but you can see that the water is really trying to get away from the oil. They don't like each other. And why this is because water is polar and oil is nonpolar. So we talked a little bit about polar before, but we didn't really talk about nonpolar. So here's an image of water, and here's an image of some kind of fat that's not, well, I guess it's more of like a hydrocarbon. So this is ethane. If you were playing with the models in class, you were using ethane. But you could kind of extend this and make this like 10 carbons long with hydrogen, or 20, or 12 or 8 or whatever you want it to be. As long as it's a hydrocarbon, you're kind of thinking just like in terms of fat. So you can see here, this molecule is polar. Okay, here's its dipole. You can see the charges that I put them on these diagrams. So this is a negative charge here, so partial negative. Okay, so it's negative 0.86, and these are a little bit positive. Here in our hydrocarbon, there is even sharing of electrons. This is a nonpolar molecule. So what does nonpolar mean? Nonpolar means that the electrons are shared equally, and when electrons are shared equally, there's not going to be a charge distribution. The negative charge is going to be evenly shared throughout that molecule, so there's not going to be any places that are partially positive or partially negative. There could be like just random, and like when you're kind of probably thinking about like in your back of your mind, like London dispersion forces, when the molecule gets big enough, you can get kind of that random moment. But in general, okay, these are nonpolar covalent bonds, and it's going to be relatively equal sharing. So when we think about how these molecules interact with water, we use the two terms hydrophobic and hydrophilic. So hydrophilic are water loving, okay, because we want to think about how everything relates to water because water is so important. So anything that really likes water, we call hydrophilic. Okay, break it down, hydro, water, phil, okay, means you like, love. So things that typically love water are things that are polar or maybe slightly polar, and these things are going to be really easy to kind of mix with water really nicely. Something that's hydrophobic will be water-fearing. Okay, so in this case, something like ethane or something like this oil that's in this beaker really doesn't like water, so they try to stay apart as much as possible. Hopefully you've heard the term like dissolves like. Things that like each other like to hang out together. Things that don't like each other try to stay apart. So we want to think about how things interact with water throughout the year, because it's going to be really important when we talk about proteins and lots of other molecules coming forward in class. So you may have seen this diagram, but I think it's really helpful, and I just wanted to bring it up from some students may have this from chemistry last year, but it can be really helpful for knowing if a molecule might be polar or nonpolar, and then what kind of force would be acting upon it. Typically, we're going to be really focusing on hydrogen bonding. Is something going to be hydrogen bonding with water or hydrogen bonding with something else? So we're going to really be focusing on kind of the difference between things being polar and nonpolar. Okay, so in class, there's also a simulation that you had to go through. So this simulation focused on a little bit on ethanol and also a little bit on a bigger molecule that's kind of like maybe something that we would call like a fatty acid. And we'll spend a little bit of time talking about those. So looking at these two molecules down here, thinking about intramolecular forces, we want to think about kind of what's going on inside this molecule. How is it going to interact with water based on what we see here? So you had the models. If you were in class, you had models to play with. I'm just going to hold up a model for a second. Give me 1 second. I didn't grab it yet. Sorry about that. So you had water molecules to play with in class. So these are really cool. They have they kind of magnets in them to simulate how hydrogen bonds form. Okay, partial positive to partial negative. You got to play with the ethane, no interaction. Remember, they repel based on our last slide. But the next thing that you got to play with is ethanol. So ethanol is really kind of cool. It's similar to ethane, but it has an alcohol group on it, an OH. So now there's that really electronegative oxygen. So if you put these together, you can see that the partial positive of a water molecule is attracted to that partial negative of the oxygen. Okay, and the partial positive of the hydrogen on the alcohol group is attracted to the oxygen of water, okay, because it's partial negative. If you try to interact this side of the molecule, nothing happens. There's water, it's raining. So if we're looking just and thinking about ethanol for a second, we have some polar covalent bonds, and we also have nonpolar covalent bonds. This molecule does form a pretty good dipole, though, so there will be some charge distribution on this alcohol group, and it will interact with water. If you look at something like caprylic acid, I have a picture of it on the bottom down here. Caprylic acid really has a lot more carbon in it, and it has a lot more carbon-carbon bonds and carbon-hydrogen bonds, a lot more non-polar covalent bonds. There are definitely some polar covalent bonds on this end, but a lot more non-polar covalent bonds. So there are places that this molecule could be attracted to water, but in general, it really has a lot of nonpolar covalent bonds. So will ethanol form hydrogen bonds with water? You bet it will, pretty easily. Will this caprylic acid form hydrogen bonds? It could, but there's a very small portion of the molecule that does. So if you look over at this simulation that you had to run, I just have a snapshot of it, you can see this molecule really is just kind of orienting itself with those polar covalent areas of the molecule facing the water, and then the non-polar areas in the oil. So some of these molecules, they aren't really one or the other. It's not just non-polar, it's not just polar. Some molecules, like this caprylic acid, have properties of both. And this is something we're going to spend a little bit of time talking about. In general, though, this molecule is mostly nonpolar, and it's going to behave, it's going to prefer to be an oil if possible. But if there is some type of interface with an aqueous solution and oil, this molecule is going to orient itself in a certain way to lower its potential energy and kind of be in its happiest place. So we're going to come back to this idea a little bit more when we talk about membranes. So kind of tuck that back, but I wanted you to start thinking about it now. So this is water. Please bring any questions that you have with you for next time. And also, the next slide. On a piece of paper, draw 3 water molecules and show me how they interact with each other. Okay, that's going to prove that you understand hydrogen bonding and cohesion. So I will see you guys next time and bring questions with you.